Okay. You guys ready to pick up where we were? That's okay?
Yeah.
Okay.
Professor, I had to mention something to Marco speaking.
Yeah.
I have a mandatory meeting for my major class at like 2 o'clock.
Okay.
So if I leave class, I know you posted the recording for this. Or
Yeah, don't. I appreciate you letting me know. Don't even stress about it. Okay.
Thank you.
Yeah, so I'll post this. I'm going to have 2 different recordings now because I had to break and end the meeting. So I'll post the 2 recordings from this class as well as the recording from my other class. Okay.
Okay. What's the homework again?
So the homework, your next homework assignment, I'm going to post next week. So if we just quickly look here at our course syllabus. So after next class, I'm going to post your next homework assignment. So it'll be on basically what I covered today and next class.
Okay.
Okay. Next class is going to be a really, really important one. I don't know if you guys ever noticed this about this class, but a lot of times what I do is I show you how to do stuff by hand, and then I show you how to do it with your calculator. So next class, what I'm going to do is I'm going to show you, to go back to this, how to do a lot of the stuff we talk about at the end of this class with your graphing calculator. So next class will be really, really important. Okay, so just to be clear, audio is a lot better.
Yeah.
Okay, sorry. I'll write Airbnb a letter and, I don't know what I'll say, but I'll just say internet was spotty. Okay. So here's where we are. We were talking about this uniform distribution stuff, okay? And so we said, let X be the time spent waiting for your packages between 0 and 60. So now I want to find the probability density function for this random variable X. So it's this thing right here. Do you notice how you have your A and B, your ending and starting values? So this 0 is my A, and this 60 is my B. Okay, so my probability density function, f of X, it's going to be a piecewise defined function. Now it's 1 divided by, can anybody tell me what minus what?
B minus A.
Which is what minus what in this case?
60 minus 0.
Okay. And this is for whenever you're between 0 and 60, and it's 0 otherwise. Okay. So you could just leave this as 60 minus 0, or you can even just clean it up a little bit and just write it as 1 over 60. This is for 0 between 0 and 60 and 0 otherwise. But like, is this not, doesn't seem too bad now? I know the definitions were crazy, but does it just not seem too bad anymore? You see it like this? Okay, we got 1, yeah. And then we're gonna do another example too, okay? So the next question is, what is the density curve for the random variable? So the density curve is this right here, okay? So draw the first quadrant of the Cartesian plane. So X here, the random variable, X is just the time spent waiting. For your package. And then the vertical axis just gets f of X here. All right, so f of X, that's this value right here, 1 over 60. So I'm just gonna put here 1 divided by 60, okay? Now the possible values of X are everything between 0 and 60. Okay, so here's 0, and I don't know, 60 will be way out here. This is obviously not drawn to scale. And then looking back, It's just a horizontal line over those possible values. And then once you're outside these values, it's just equal to 0. So literally, this is what I did. Vertical axis gets 1 over b minus a, and then it's just a horizontal line between the possible values. Pretty straightforward. Not too bad, at least. Don't worry, we'll do another example too. Okay. Is everybody okay if I move on for a second then? Okay. Remember, the most important thing here, okay, the most important thing is we're going to relate area under the curve to probability. So now here was the question. What is the probability the package arrives sometime between 10 a.m. and 10:30? Okay. Probability package arrives between 10 and 10:30. So if it arrives at 10, you waited for 0 minutes. If it arrives at 10:30, you waited 30 minutes. All right, what did we say that this probability was? What did we say this answer was going to be equal to? Does anybody remember? Okay, thank you. Yep, perfect. It's going to be equal to 1/2 or 50%. So here's how you do this, how we're going to do this stuff going forward, okay? To answer these questions going forward, they're not all going to be this simple, okay? I just really started with a simple example so you can understand the process. You're going to sketch the density curve. And you're going to shade in the area under the curve between the two values of interest. Okay, in this case, the values of interest are 0 and 30. Okay, so the first thing we're going to do is we're going to sketch this density curve. So what I'm going to do here on my graph or on my slide here is I'm going to re-sketch the density curve. Okay, it was x. Here was f of x. You had 1 over 60, 0 to 60. Like this. Okay. Oh no, my son woke up from his nap. Shucks, I have to finish teaching. My poor wife's gonna have to get him. No LOL there? Okay, no big deal. Yeah, he hates naps. Okay. Okay, so here's 0, 30 falls between here, okay? So what I'm gonna do is I'm gonna draw a line up till I hit this graph, and then I'm gonna shade in this area here, okay? What shape do I have here? What does it look like?
A rectangle.
Yep, it's a rectangle. Okay, so what I'm saying here is this area is the answer to this problem. So how do you find the area of a rectangle? It's length times what?
The width.
So the length of this rectangle, what is the length from 0 to 30? How many units is that? It's 30, right? And the width is from here to here. So what is this width right here? Isn't it just the height of the graph here? So it's 30 times 1 over 60. Well, think of 30 as 30 over 1. 30 times 1 is 30. 1 times 60 is 60. And what is 30 over 60 reduced to? What do you guys think?
1/2.
Boom. Isn't that what we said the answer would be?
Yes, sir.
Hey, looking back, we said all the way at the start. The answer should be 1/2. And now we related area under the curve and got the same thing. Isn't that crazy? You guys think that's crazy or what? Not crazy? I think it's super interesting.
Yeah, it's pretty crazy.
I like the I like the visual graph, not the whole numbers, you know, up top.
I hear you. I hear you. All right, let's do, is everybody okay if I move on and we'll do another question related to this package?
Yeah,
Everybody good?
yeah.
All right, so let's do a follow-up question here. Same problem, okay? What is the probability the package arrives sometime between 10:30 and 10:45 a.m.? Okay. So first off, if it shows up at 10:30, how many minutes were you waiting?
0.
No, remember it said the package said it could show up between 10 and 11. Yep. So
Oh, all right, so 30.
okay. And then if it shows up at 10:45,
45.
okay. So what we're always going to do to answer these questions, okay, for continuous random variables, we're going to sketch the density curve and shade in the area, okay? So let's sketch the density curve. So the density curve is still the same exact one for this problem. Okay, got the random variable x, and we got f of x. So x could be any value between 0 and 60, and its probability, or the value of the PDF here was 1 over 60. And then you're just going to draw a horizontal line, just like that. And now I want to be between 30, and then here's 45. So I'm going to shade in the area under the graph between those values. All right, can anybody tell me what the length of this rectangle is right here?
$15.
Yep. Can anybody tell me what the width is?
1 over 60.
Thank you. So this is just 15 times 1 over 60, which is 15 over 60, which simplifies to 1/4, or 0.25. And I think that totally makes sense because that's a 15-minute window out of a 60-minute window total. So the probability shows up in that 15-minute window is 0.25. So what do you guys think? Not too bad seeing it now?
It's so much easier with the numbers.
Totally easy with the numbers, right?
Yeah.
Okay. All right, so I want to do one more example real quick. And this was the example I gave on last year's exam, okay? So you can see exactly how this problem will now look on an exam, okay, or on your homework, all right? You guys ready for another one?
Yeah.
Okay. Let's do one more. All right. Does anybody ever take the bus to campus, just out of curiosity? I do I do at least once a year, sometimes twice a year. Okay, yeah, yep, the number 40 bus, yep. Whenever I'm in White Plains, I always hop the number 40 bus to get to campus. Okay, I fly there, okay. All right, so here's the example, okay? Suppose the travel time from White Plains Transit Center to SUNY WCC on public transit, so bus route number 40, which is a real bus route, okay, follows a uniform distribution, okay? So whenever you see this uniform distribution, it's just going to be like the previous example, okay? With a minimum amount of time of 12 minutes and a maximum amount of time of 22 minutes, okay? So the quickest it could get there is 12 minutes, and sometimes because of traffic, it takes 22 minutes, but everything in between there follows a uniform distribution, okay? So let's let the random variable X represent the time from White Plains Transit Center to SUNY WCC on public transit, okay? So this is what I'm gonna do. I'm gonna start by saying let X be equal to the time spent on public transit from White Plains Transit Center to WCC. What is the least amount of time that you could be on the bus? Like if everything goes perfectly, what did they say the minimum amount of time was? Okay, what is the maximum amount of time? Okay, so X has to be, would you guys agree that X has to be between 12 and 22? Yep. So think about now you can start to see where things are falling into place. Uniform distribution. This is my starting value A, and this is my ending value B. Okay. See how it kind of, starts making sense now? I hope it does at least. Okay. All right, is everybody okay if I move on? Everybody good? All right, so now I'm gonna ask you some questions. Okay, 3 questions here real quick. What is the probability density function PDF for the random variable X? Okay, so we know it's a uniform, so I'm gonna write it like this. X follows, in statistics, this squiggly line means follows a uniform distribution. So the probability density function, f of X, whenever it's a uniform, is just this piecewise defined function, okay? So going back, it is always this right here. Always, always, always. So for our problem here, it's 1 divided by what minus what? Yep, and what's my, yep, thank you, in the chat there, yep. 22 minus 12, and this is 4. 12 less than or equal to X, less than or equal to 22, and 0 otherwise. All right, let me clean this up so it looks even nicer, okay? What is 22 minus 12? Yep, so this is just 1 over 10 whenever you're between 12 and 22, and it's 0 otherwise. Okay. Pretty easy now that you've seen it like this? Yeah, okay. Now let's sketch the density curve for this, okay?
what does it mean by the zero otherwise?
So it just means like, let me go back and show you. Good question.
Doesn't that apply to the situation?
Sorry?
Doesn't the zero otherwise apply to a certain situation?
Yep, so what this means is, like, looking back here, it just means, do you notice, like, do you guys see this graph right here? You see where I'm pointing here? What the zero otherwise means is the graph is equal to 0 along the vertical axis here. And it basically what it means is, look, there's no possible value outside of A and B, okay? So like for this example here, what this means is, look, the bus will never, the probability that the bus gets there quicker than 12 minutes is 0. Like it just won't happen. The probability that the bus gets there greater than 22 minutes is 0. It won't happen. Like just for whatever reason, we'll just assume like the bus just always runs on time and it just will never take more than 22 minutes. That's what the 0 otherwise means, is whenever you're outside of 12 and 22, just 0, not going to happen. Does that help make sense what that 0 otherwise means?
Yes.
Okay. So now the density curve for this. So you get X down here, okay, which is time spent on bus or public transit. And you get f of X up here, okay. Well, so here's 0. What was the minimum time again that you could spend on the bus? Yep, what's the maximum time? And then here's 1/10. So this is how it works. As soon as you get to the value 12 and you get out to 22, there's the graph. And then when you're outside of that, it just can't happen. The probability is 0. Like that. All right.
So compared to the other example that you gave us, we started at 0 because it started at 10, right?
So in the previous example, we started at 0 because, yes, because we said start counting as soon as it hit 10. So theoretically, the package could show up at 10 and you waited 0 minutes.
Okay.
Here we're starting at 12 because like you have to be on the bus at least 12 minutes.
Okay.
So it just depends on the problem. All right, so now what is the probability the travel time is between 15 and 18 minutes, okay? So this is the probability that, hey, you're between 15 and 18 minutes, okay? So let me go to 15. Here's 18. I'm going to shade the area under the curve. Like this. So this is equal to length times width. Well, what is the length from 15? So you shade under the density curve when you want to find a probability.
3 times 1/10.
Yep. So the length here is 3. And the width is 1/10.
3/10.
Yep. Thank you. And that's it. Makes not, so I can't tell, not too bad, bad. Could you handle one of these on the homework? Now that I've done 2 examples. Okay. That's okay. You know what? So I'm going to post the homework for next class. And, what I'll do is I'll, just like we did before with the previous homeworks, like just if you come to class with questions, I'll help you out with them. Does that sound okay? Okay. All right, let's move on. So But I want to spend we're going to get away from the uniform distribution now. So the only reason I really introduced the uniform distribution is to illustrate the idea of this area under the curve, excuse me, between two values is equal to the probability that you observe a value between these two numbers, okay? So just area under the curve is equal to the probability. That's the whole key concept here. So the uniform distribution is not often used in the real world. Like there's just not too many like real world applications for it, to be honest with you. So a more common distribution in the real world is the normal distribution. So how, just out of curiosity, have people heard of the normal distribution before? Has anybody heard of this before? Got one, yes. How about this? Let's see if another one. It's also sometimes referred to as the bell curve. Okay, have you guys heard of that before? Bell curve? Yeah, okay. Well, the bell curve looks like this. Well, that's not too bad, okay? So this is this concept of the bell curve, okay? And if you notice, what we're gonna do is now we're gonna relate PDF density curve to this normal distribution here. But what's a little bit harder is like, I'm just gonna go back one slide, is finding the area under this curve is really easy because it's just a rectangle. Like the area of this rectangle is length times width. This is not a nice rectangle, okay? So we're gonna need like another way to find area under this curve. And this is where it gets a little bit complicated. And this is what we're gonna spend this class with, the rest of the 30 minutes we have left in class talking about, and then all of next class doing. So what I'm gonna do is today's class, the remaining time, I'm gonna show you how to find area under the curve using a trick or properties. Next class, I'm gonna start by showing you how to do it by hand with learning how to read your first statistical table, which is awesome. And then when everyone's like, why don't you just lead with this? And then I'm going to show you eventually how to use your graphing calculator to make all this stuff a little bit easier, okay? But what I found, and I don't know if you guys agree, is that after I show you how to do it by hand, it helps you with your understanding of the graphing calculator a little bit. I hope you agree with that, I'm not sure. Yay, calculator, yes, okay. So here's a definition. Okay, so a continuous random variable X is said to be normally distributed. So what I'll do is I'll write it like this. I'll say X, and whenever you see the squiggly line, it means follows or is approximately normally distributed. Like if you just look at the frequency histogram of this, and it has the shape of a normal curve, okay? So let me just show you something like this, okay? Everybody okay if I go to the next slide? Everybody good? All right. So like, here's an example, okay? So frequency histograms that are symmetric and bell-shaped, like you can see the bell-shaped curve here, all right, is said to be the shape of a normal curve. Okay, so like bell-shaped here. Okay, and it doesn't have to be perfect, but just like as long as you can superimpose this bell curve on top of it, okay? This tells you that whatever this random variable is, this data follows a normal distribution. Okay. And now what we're going to do is we're going to just spend a ton of time talking about the density curve and the probability density function for these type of distributions. Okay. All right. So when a random variable X is normally distributed, so not uniform, but follows this bell curve, all right, we can model the variable using what's called the normal density curve. Okay. And so just recall, like a uniform, it just looked like this, okay? It was just this, whoop, just this horizontal line. But now what we're going to be doing, instead of this just straight horizontal line, all right, we're going to be drawing this bell-shaped curve, okay? Bell-shaped, okay? So the normal is going to look like this going forward. You're going to notice when I do these normal curves, I'm no longer going to put the vertical axis on it. I'm just going to draw the horizontal line. Well, that's terrible, okay? But you guys get the idea. So it's going to just be this bell-shaped curve. All right, so the normal probability density function, the equation for it, is given by this crazy equation here. Okay, does this look easy to work with right here? Okay, does this equation look like terrible? Like it's equal to 1 divided by the square root of 2 pi sigma squared, the number e, which is the exponential, raised to the negative x minus mu squared divided by 2 sigma squared. Okay, kill me. We don't have to, okay? Okay, it looks crazy hard, okay? All right. And so I'll be honest with you, which is great, okay? We're never going to use this equation, all right? The last time I actually had to use this equation was actually in graduate school. I had a graduate level class that made us work with this equation. So I'm not, obviously we're not going to work with it in a 100, introductory statistics course. But what I want you to know is that when we draw these normal bell curves, okay, there is an equation behind it. They're not just some fancy graph that we put up there. There's a mathematical equation behind it. And this right here is the mathematical equation, okay? So instead, okay, of working with the normal PDF like this, is everybody okay if I go on to the next slide? Okay. Okay, so yes, the equation is scary, all right? Even I don't want to work with it right now, okay? Don't worry, we'll work problems using the following ways, okay? All right, the first one is the graphs and properties of the normal curve. Okay, this is what today's remaining lecture is going to be about. And then next class, I'm going to show you how to do the following, okay? I'm going to show you how to do problems by hand, okay, with using a statistical table. And then I'm going to show you how to do it using your graphing calculator, okay? And then when you finally get to like exam day, okay, in a couple weeks, you'll be able to do the problems with your graphing calculator. Okay, so I think like do you remember when we did the binomial probability distribution? I showed you how to do the equation by hand, and then I said, oh, okay, by the way, there's an easy way in your calculator. And those problems I think became not too bad. It's the same way with this, same way. All right, so let's, with the time we have left today, let's talk about the properties of the normal curve, okay? Everybody okay if I move on? Okay. All right, so here are the properties of the normal curve. All right, so properties of this normal density curve. The first one is the curve is symmetric about the mean. Okay, what does this word symmetric mean? Does anybody know in mathematics what it means? All right, I'll try to explain it. Hey, that actually looks pretty good, right? What do you guys think? That curve looked pretty good? The answer is yes, thank you. So what it means is these normal distributions will have a mean, which is going to get denoted with the Greek letter mu. What symmetric means, if I were to take this graph and whoosh, cut it down the middle and fold it on top of each other, they would be mirror reflections of each other. So they're like perfect mirror images of each other. Okay, that's what symmetric means. The second one, when something's normally distributed, the three measures of central tendency, the mean, median, and mode, okay, are all equal to each other. and the curve has a single peak, and its highest point of the graph here, okay, this highest point occurs with whatever the value of the mean is. And that'll make more sense when we start drawing them, okay? The third property, okay, the total area under this curve across all possible values is equal to 1. So again, that's how we relate it to probability. Okay. And next, all right, the area under the curve to the right of the mean is equal to the area under the curve to the left of the mean, which is equal to 1/2. Okay. So what this means is half the area is above and half is below. Okay. Everybody okay if I go on to the next slide? Okay. Fifth property here, as x increases without bound, all right, gets larger and larger, okay? The graph approaches but never touches the horizontal axis. And it's the same thing, as x decreases without bound, gets more negative and negative, the graph approaches but never touches the horizontal axis. What this means is that when we draw these graphs, they're going to get really, really close to the horizontal axis but never touch it. Okay, it's going to go just like this. Okay, what this means is the horizontal axis is an asymptote for the graph. Okay, has anybody ever heard of the term asymptote before in mathematics? Yeah, pre-calc. If you haven't, that's okay. It just means the graph like butts up against it. Okay, like it gets infinitesimally close to the graph, but never crosses it or touches it. All right, and what we're going to use in class today with the time we have left is just this empirical rule. This is the most important thing. Okay, and what it goes like is this. All right, approximately 68% of the total area under the curve is between the mean and take away a standard deviation to the mean plus a standard deviation. Okay. You guys remember we talked, this has been a while. Okay. But does anybody remember when we talked about this empirical rule? Like probably about a month ago now? One person remembers. It's okay if you forgot. It's not a big deal. It was just a real brief footnote on a slide. Okay. I'm going to show you the best way to do this is to just print out the PowerPoints, and don't stress. And a lot of this is like once you see the first example, it's going to be a piece of cake. I promise you. Okay. The next rule here is approximately 95%. 95% of the area is between, you take the mean and you subtract 2 standard deviations, and the mean and you add 2 standard deviations. And then if instead of 2 standard deviations, you go 3 standard deviations, 99.7% of the area is between the mean and subtract 3 standard deviations and the mean and add 3 standard deviations. Okay. This next graphic I'm going to show you is the most important graphic for this class for the rest of this time, okay? So I'm going to show you the empirical rule number 6 graphically. Okay, so don't stress about writing this down right now, okay? Is everybody okay if I move on for a second? What I would do if I were you is I would print this out and have this handy as I go through I'll do another review problem of this next class, okay? But this is the most important visual representation of the empirical rule, okay? So when you have a normal distribution, you're going to be given a mean, okay? And what we're saying here is you take the mean and you subtract a standard deviation from it, and you take the mean and you add a standard deviation. 68%. Okay, that's good. 68% of the observations, or the 60% of the data, will fall within one standard deviation of the mean. Okay. So because the curve is symmetric, when you take 68% and divide it in half, that means 34% goes from here to here, and 34% math instruction. I've never heard of that, but is that a website or something in the chat there? Yeah. So 34% will fall below the mean and to one standard deviation, and 34% from the mean to here. Okay, because the total area under the curve is 1, that means this area from here to here is 0.34, and this area from here to here is 0.34. That's okay. I also have a YouTube channel, but I encourage you to check that one out. So we can go on then, okay? There was something like this very briefly on test 1. We covered it, but this is basically really what the next section is going to be entirely about, okay? I just want to get through this real quickly and then do one example so you can understand how we're going to use this, okay? So I said within 2 standard deviations of the mean. So if you take the mean, I appreciate that. And go out 2 standard deviations from above or below. So here's 2. 95% will fall between that area. It's okay. So if you take 95% and divide that in half, from here to here, this total area under the curve would be 0.475. Okay, that's how I got this 34% plus 13.5%. Okay. That's also saying the area between the mean and 1 standard deviation and the mean and 2 standard deviations is 0.135. And it's the same thing on the other side. All right. And you can keep going and see how you get out to 3 standard deviations and so on. All right. Don't stress. Does everyone feel like they're drinking from a fire hose right now with this stuff? Like it's just so much information thrown at you? Okay. But you know what's great? And I promise you, like, what did you feel like when I started the uniform distribution? It was like, what the heck is Matt talking about? And then after you saw the first numerical example, it was like, oh, okay, I get what Matt was talking about. It's going to be the same thing here. All right. So just bear with me. Okay. Sound okay? All right, so just a few quick other things before we get into the first example. All right, here you have 2 different normal curves. Okay, here's the mean is 0, standard deviation is 1. Here's the mean is 3 and standard deviation of 1. Notice how they're the exact same curve. They're just centered at different values. Like when the mean is 0, the curve is centered at 0. When the mean is 3, the curve is centered at 3. Now here's 2 different normal curves. Both have an average of 0. But notice how this one has a standard deviation of 1 and this one has a standard deviation of 2. The curve that has a smaller standard deviation still has the bell-shaped curve. It's just taller. This one here that has a standard deviation of 2 still has the bell-shaped curve, but it just looks shorter and wider, okay? So these normal curves can all look different depending on their mean and standard deviation. You know, they could be short or they could be tall and skinny or short and wide, but they all still have this bell-shaped curve, okay? All still have the bell-shaped distribution. Now I just want to do one example with the time we have left, so this can all make sense to you. I've got 19 minutes, so I'm going to crack my knuckles, all right? And let's do this problem. okay? Have you guys heard of this phone called an iPhone? You guys know what I'm talking about? That was a joke. Everyone's heard of an iPhone, right? Okay. All right. So, suppose talk time. So what talk time is on a phone is if like you were to pick up your phone and it was at 100% and you were to call somebody and you were to talk to them nonstop, how long it would take until the phone died. Okay, that's what talk time is, right? So suppose talk time on this iPhone 10 is normally distributed, okay? So whenever you see this normally distributed, it tells you it's going to be a bell curve problem, okay? With a mean of 20 hours, okay? So that's this mu and standard deviation of 5 hours, okay? That's this sigma. All right. Suppose an iPhone 10 is selected at random and its talk time is recorded, okay? Do I know, when I pick, let me ask you this. Do you think every iPhone 10 has exactly the same talk time? Like every iPhone 10 out there will last exactly the same amount of time? Yeah, like no, right? Like there's so many variables that go into it, right? Like how old it is, how many apps you have on it, things like that. So I'm going to define this variable. I'm going to let the variable x be the talk time on a randomly selected iPhone 10. Okay. Now, did I say how talk time was distributed or what talk time follows? Did I say it follows a normal? Yeah, look, like the problem right here. It's going to tell you it's normally distributed. So I'm going to write x is normally distributed. So instead of that uniform distribution, and this is incredibly important, okay? Whenever we do these problems, literally over the next 2 weeks, I'm always going to have to tell you what the mean is. So on average, it was 20 hours. So I always will give you the mean. And this, I will always give you the standard deviation. Okay. So again, I'll always tell you it's normally distributed, then I'll give you a mean and standard deviation. Okay. Everybody okay if I move on for a second? Or move on? Or does anybody need me to keep writing? I've got one person who says yes. All right. So I just want to get through these 3 questions here with the time we have left, okay? We'll see if I can get into the rest, okay? Is X right here, this talk time, is X continuous or discrete? What do you think? Is the time spent on your phone a discrete or a continuous random variable? So is there a finite number of hours and minutes, or is it like a measurement of some type? Yeah. So time is a continuous. Okay, so this is going to be a continuous random variable. Okay. The next question says sketch the density curve. All right, so I'm going to go back. The density curve when something is normally distributed is just this bell-shaped curve. Okay, just like this. All right, so whenever we do these problems going forward now when something's normally distributed, we're just going to sketch a horizontal axis, okay? And along the horizontal axis, you're going to get X, which is the talk time on the iPhone 10. Okay. So what you're going to do then is you're going to draw this nice bell curve. Okay, mine's not too bad. Okay, it's not great, but it's not too bad. The high point of the graph, notice how I'm going to draw this dotted line down here, is going to occur at the mean. Okay, what did I say the average talk time was for the iPhone 10? Anybody remember? Yep, 20. And then look, I'm going to go back here. And what I'm going to do is I'm going to take the mean and I'm going to add a standard deviation, then I'm going to add it again, then I'm going to add another, and I'm going to subtract and subtract and subtract. What did I say the standard deviation was? Yep. So if I take 20 plus, yep, thank you. Yep, 5, I get 25. I'm going to draw a little here. If I add another one, I get 30. And then if I add another one, I get 35. Now I'm going to subtract it. If I subtract 5 from 20, I get 15. I'm going to subtract another one, I get 10. Yep. And then I subtract another one and I get 5. So now I know this, I'm going to just go back. Don't worry, I'm going to come back. Look at what I have here, okay? Does this curve here with these numbers look like this here, but just filled out with actual numbers instead of these crazy symbols? Yeah. Okay, great. So now I'm just going to ask you a probability question, okay? What is the probability that the talk time for randomly selected iPhone 10 is between 10 hours and 25 hours? So it's the probability that it's between 10 and 25. So that talk time is between 10 and 25. All right, guess what? I have a density curve. What I'm going to do is I'm going to shade in some area and I'm going to use that empirical rule to help me solve it. So what I'm going to do here is I'm actually going to redraw this just so you have this nice and neat in your notes and when I post it online. Okay, this one didn't come out as well. Actually, this one's pretty terrible. Sorry. You're supposed to say in chat, no, Matt, it still looks okay. No, it's too late. I had to prompt that. Okay. So here's what you're going to do. All right. You're going to shade in the area you're interested in, right? So I want to be between 10, which is right here, and 25, which is out here. So I want to find this area, and this area here. Okay, so notice how this is not like a rectangle, okay? So we're gonna have to go back. You don't need to multiply the percentages. Just watch what I do to solve this, okay? So to answer this, to find this area here, we're gonna have to go back and use this rule here, okay? So to go from 20 to 15 and down to 10 is how many standard deviations? Two, right? Yep, 2 standard deviations. The standard deviation is 5, but to go from, that's 1 standard deviation, 2 standard deviations. So let's look here. To go from the mean to 1 standard deviation is right here, the mean to 1 standard deviation. That area is 0.34, okay? Does everybody see that right here? So that means this shaded area right here is 0.34. Now I want to find between 10 and 15. Well, that's from 1 to 2 standard deviations. So let me go back to my property here. 1 to 2 standard deviations. Holy cow, look, that area right there is 0.135. Does that make sense? Because this to this is this area right here. So this little part here is 0.135. But now I got to find from 20 to 25. So going back to my list, that's the mean to 1 standard deviation. That's this light turquoise area here, which is 0.35 or 0.34, excuse me. So what do you think I should do with all these numbers here? Add them. We want to add them. Yeah, you want to add them because what take this area plus this area plus this area is the total area. Does anybody know what you get when you add all these up? Is it is it 815? Did I do that right? Thank you. Thank you. And that's the answer right there.
So for each time you ask a question like that, we have to go back to that bell curve thing reference.
Yes.
And
Yep.
see.
Let me just do one more problem and then I'll talk about where we're going to go from here, okay? I'm going to talk about it in 1 second. You do not have to memorize that curve. No. Okay. Let me just do one last one, okay? Because we have a couple minutes left. Is everybody okay if I go on for a second? Okay. So the next question is, what is the probability the talk time is between 25 and 30 hours? Okay. So I want to find the probability that the talk time is between 25 and 30 hours. So again, you're just going to sketch the density curve. You're centered at 20. Let me do those standard deviations. So add 5, 30, add another 5, add another 5, 35. Subtract 5, 15, 10, 5. And I want to be between, look, 25 and 30. Here's 25, here's 30. I want to be that little red shaded area right there. Okay. Well, this is between 1 and 2 standard deviations right here. Okay. So if you're copying, just pause for a second. Okay. So this is 1 standard between 1 and 2 standard deviations away. So I'm going to go back to this chart here. Can anybody tell me what the area is between 1 and 2 standard deviations from the mean? What is it here? Is it 0.135? Yeah, right there. And that's all you're doing for this chart. Okay. Does that make a little sense? I got 1 yes. Everybody else like, is class over with yet? All right. Let me just say one thing. you do not have to memorize this, okay? So actually, I'm gonna ask you problems. We're gonna do a couple more of these next class so that you can see how to use this empirical rule. But yeah, this is the last question for today. I'm gonna pick it up next class. I just wanna say a few things, okay? With the time we have left. And then I'll pick up class next time with this exact example, okay? And then don't worry, then and then I'm gonna have a couple more problems in the next lecture for you guys, okay? This stuff right here, we actually aren't gonna do too much because like, what if I asked you this question? What is the probability the talk time is less than 18 hours? Okay, does 18 fall on a nice standard deviation? No, right? So the only standard deviations are 15 and 20. Is 18 anywhere on this horizontal axis? Yeah, so like, how do we answer that question? Okay, and that's really where we're going to be driving with all this stuff. So don't stress. Do not stress too much about this empirical rule right here. Okay. What we're going to spend the entirety of the next class doing is legit more problems like this. Okay. The only difference is I'm going to show you how to do using a statistical table, which I'll post to the classroom, and then also how to use your graphing calculator. And I will also post your next homework for you, so you'll get a chance to try this next week. All right, I'm going to stop the lecture or stop the recording.